Okay, before the break, we did the full derivation of this, the generalized time and transfer constant. So we saw that all the terms of this transfer function can be calculated exactly using a combination of time constants and transfer constants. And we, again, to refresh your memory on the notation, the subscript is the subscript associated with the element, and the superscript is the indices of the elements that are infinite valued. So now let's look at a special case of this first, and then we'll use the general case. And the special case we are going to look at is the second order system. So let's say we generally have a second order system, right? So this would be, again, a simple case relative to what we had before. So let's say you have a transfer function. So this is a second order system, which is of the form a0 plus a1s plus a2s squared divided by 1 plus b1s plus b2s squared. And we know what these coefficients should be. So we know a0 is the transfer constant. So here, basically, the system we're talking about has only two elements, two energy storage elements. So we can call it, let's say if they were both capacitors, they can be inductor and capacitor, doesn't matter. I'm just showing them as capacitors here, and no dynamics inside. Input X, output Y. So A0 is H0, sorry. H0 here, which basically means when you set both the elements to 0 value. In this case, both of them would be open circuit. If one of them was an inductor, that would become short circuit, and you see what the transfer function from the input to output is. A1 would be what? Or let's start with B1, according to what we have there. So B1 is the sum of the time constants. So now the index in this case goes from 1 to 2. Zero value time constants. Now, what are the zero value time constants? So it's tau 10 plus tau 20. The time constant associated with element 1 when the other element and the independent sources are 0. And the resistance seen here times that capacitor, or if it were an inductor, the inductance divided by that resistance. And the same thing for the other one. Now, A1 is going to be the sum of these tau I0 Hi, which would become tau 10 H1 plus tau 20 H2. And B2, now let's see what this is kind of a new one now, right? This is something we know. So what is B2? Let's write those sums explicitly and see what it reduces to. So the sum explicitly, if you write it exactly, is this. Greater than 1, or greater than or equal 1, smaller than or equal 2. So how many of tau I0 tau Ji? So how many terms are there in this sum? Just one, right? It looks like a big thing, but it's really nothing. It's just one. I mean, it's not nothing. It's just one term. It's tau I0, tau 10, tau 21. But also, since the indices of the elements should not matter, this has to be equal. We argue that it has to be equal to tau 20, tau 12. Right? So that there's an equality. So there are really 3 degrees of freedom here in the time constants, not 4. And really, you need to do 3 calculations. You need to know for the B's coefficients, right? You need the tau 10, tau 20, and one of the tau 21 or tau 12. Because the one you pick has the associated, these two have already been calculated. These are the zero value time constants, right? So if you pick one of them, you know this product, what this product is. And we'll just, in a couple of examples, we'll do both, so you can see that that product actually is equal. But in general, you have a choice. And you can actually, if you're clever about it, you can pick the one that's easier to calculate. You can say, OK, well, if I short circuit element 1, the circuit becomes really simple. Or if I short circuit element 2, the circuit becomes really simple. So then I use that one. Because the objective is not to make your life more difficult. It's just for you to provide some insight about what's happening in the circuit. So there are this kind of interesting thing. And then, of course, the B2, if you want to calculate, A2 for completeness, A2 would have to be what? Would be, again, the similar kind of awful looking sum, but it's not that bad. Ji, Hij, which would be what? Tau 10, tau 21 H12, which will, again, by equality, it has to be tau 2 is the same thing as tau 20, tau 1, by symmetry, not by symmetry, it has to be equal to this. So it's a single term for a second order system, right? So let's do a couple of examples. I'm going to leave this part clean because we are going to do something here in a little while. But let's go and do a few examples. So always pick, whenever you want to verify something, look how it works. Always pick simple examples first. Start with simple examples, see how they work, look at the evolution of that, and then do more examples. So let's do the first example is an RC circuit, a passive circuit really. Let's call this R1, C1, and then C2 and R2, and this is the output. By the way, is it a meaningless question? Is it a meaningful question? Sorry, meaningful question. If I show you a circuit, just the network, and if I show you a network of capacitors and resistors, right? If I show you some capacitor and resistor network, and if I ask you, what are the poles of this circuit? It's kind of an okay question. What are the natural frequencies of this network? You can do it. I mean, of course, you have to think about if your independent sources are shorting it or opening. You have to have nulled the independent sources properly. In this case, I have, because I short-circuited this guy, so it reduced to this thing. Is it also a meaningful question to ask, what are the zeros of this circuit? No, because it's dependent on the choice of the input and output. Depends on where you're looking. The zeros, if you take your output from here versus where you take it from here, or from here versus there, are different, as indicated by the presence of the H, the transfer constants in the A coefficient, but not in the B coefficients. Right? You have an H thing, a transfer constant in the numerator terms, but not in the denominator. So that's something to keep in mind. Okay, so let's do the example properly. Okay, so what are the things I need to calculate? So first things, I would calculate the first thing. So first of all, look at this, see how many poles or how many zeros do I expect from our test, which we haven't really proven, but we can actually now prove based on that. I'll do it in a few minutes. But the test that we've developed for knowing how many poles, how many zeros, where they are, et cetera, et cetera. How many poles? Two. We can define two initial conditions. I can set this to 1 volt and set this to 357 volts, and nothing will happen, right? I have 2 degrees of freedom. Now, how many zeros? One. There's the maximum number of elements that can be simultaneously infinite valued is 1, because I can only infinite value this one and get a non-zero transfer constant. Right? So I know I have 1. And is it left half plane or right half plane? That's 0. Left half plane, because the polarity of the output doesn't change when I do that. Right? Okay, so I know where I'm going. So what is my H0? What is H0? Is the transfer constant when all of the elements are 0 valued? It's 0 in this case. So you can see this is not a low pass response. In fact, this is a band pass response. But okay, so that's H0, so that's first thing we know. Then the time constants. So let's say the ZVTs, zero value time constant. What is tau 10? Tau 10 is determined by the resistance seen by this guy when everything else is, all the other reactive elements are 0 valued. So if this is 0 valued, it becomes open circuit, right? So this part is detached. This is grounded. What do you see? What is the time constant? R1, C1. And then tau 20 is what? The resistance seen by this guy when this guy is not there. R1 plus R2 times C2. Okay, thank you. So now I need to really calculate one more, but let's do both, just in case, and see if that identity holds. So let's try the tau 12. Tau 12 means look at the resistance seen by C1 when C2 is shorted. So what do you see? And of course, this is shorted. R1 parallel R2, right? You see R1 to this side and you see R2 to that side. So this is going to be R1 parallel R2 C1 because this is tau 1. And then how about tau 2-1? This is really redundant now. But we'll calculate it just to see what it looks like. Tau 2-1, what do you see? No, careful. Yes, sorry, R2, yes, correct, thank you. I have to be careful. C2, R2, C2. Yes, okay, so now let's see. First of all, let's check that identity. Let's say tau 1, 0, tau 2, 1 is what? Tau 1, 0, tau 2, 1. Tau 1, 0, tau 2, 1, sorry. So it's R1, R2, C1, C2, right? Right? Tau 1, 0, tau 2, 1. It's R1, R2, C1, C2. Or you can write it better. Oh, yeah, let's write it as R1, C1, R2, C2. Now, how about tau 2, 0, tau 1, 2? What is that? Tau 2, 0 is R1 plus R2, C1, C2. And then this guy, R1, 2. So this is the parallel combination, which is R1, R2 over R1 plus R2, C1. And these guys cancel, and you get exactly the same thing. As you should expect. Now, if you paid a little bit of attention, if you had a choice between calculating which one of these two, you would realize that if you short circuit C1, then this guy becomes very easy. So I would calculate that one. And I use this combination, which is more direct than that combination. But if you don't pay attention to it, you can still carry through it. And if you do the algebra correctly, you will get the right result. Okay? So that's a very simple example, just to show the basic concept. Now, let's do a few more examples. Okay. Let's do one more example of this nature. Okay. Let's try to do the source follower. Let's do a source follower like this. So this is another example. So let's say you have a R1. You have an R1. You have a MOSFET. The drain is connected to VDD, which is ground from an AC perspective. This is V in. This is R1 and R2. This is V out. And let's say you have two capacitors to take into account now. So let's say you are taking into account C pi and C mu. Simultaneously. So again, quick evaluation. How many poles, how many zeros do we have? Okay, how many poles? Two, right? Because you can set the initial condition on those two and they're not conflicting with each other. Let me ask another question. If I had a third capacitor here, CL, how many poles would I still have? Two, right? Because now you have a capacitive loop through here. So that would not add a new pole if you had it. Although you have 3 time constants, but it would be still 2 poles. Now, by the way, let's take a little kind of a detour. Where did this test come from? This test of how many poles, how many zeros, right? The pole, of course, is basically the number of time constants that would give you non-zero coefficient Bn, because it's the highest order. And what we did for the zero part, how did we do the zero? We said the maximum number of elements that can be simultaneously infinite valued, right? What is that number in this question, this question? Yes, right. So in this example, it's just what's the maximum number of zeros you can have? 1, right? Because you can short circuit this one and you will get some output, but if you short circuit this and that at the same time, you get nothing because you've short circuited here to ground. So where did that come from, that test? If you think about it here, look at this. Maximum number of zeros is the highest order non-zero A coefficient, right? So to get a non-zero A coefficient, that transfer constant of that order, at least one of the transfer constants of that order has to be non-zero, right? So if you have a third order, let's say H1, 2, 3, that's non-zero, it means that you will have a third order term in the numerator, which means that you have 3 zeros. That's why the test is the maximum number of elements that can be simultaneously infinite valued and produce a non-zero transfer constant. So this is where that test comes from. And I'll show you in a second also kind of like, so now that we're on that subject, also the other part was the maximum number of capacitors that, or elements that you can simultaneously set initial condition, right? So for example, why is it that the capacitive loops produce a problem, reduce the number of folds? Because think about it, if you have a capacitive loop of 3 capacitors, let's say for example, I mean just like, they don't have to be 3, and let's say each one of them has some sort of a resistor, well, it's a really ugly looking resistor. A resistor here, a resistor here, a resistor there, right? So think about the time constants, these time constants. So if I have the tau I0, tau 1, 0 is going to be non-zero, right? I'm so you have some resistance. These are going to be open circuited. You will see some resistance here and some resistance there, so you get some finite value of resistance, some non-zero value, right? Now, tau Ji, what is the time constant you see across here when this guy is shorted? That guy is shorted, this is still open, that's not a problem, right? But now let's look at the tau 1, 2, 3. If you have, this is 1, this is 2, this is 3. The resistance you see across here, if 2 and 3 are shorted, is what? 0. Is 0. That's why a capacitive loop reduces the order of the number of initial conditions by 1. You can see it, because this term will come 0 in that case. So this is exactly where those tests come from. You can see it from the equations. But we use them early on, which is fine. You can jump ahead anyway. And then use that. Anyway, so I can just leave this on, that's all. But let's go back to our example. Let's go back to our example. And so we took a little detour. And let's go back to this example and see what we get. So we can think about it also in terms of a T model. If you want to draw the T model on the side, if it helps you see things a little bit more easily. So you have the RM here. You have the ground here, IS, this is 0 at DC. And then you have the R2 to ground. You have C pi. This is really typically in MOSFETs, this is called CGS and CGD, but we just call them C pi and C mu because they're single indices, as opposed to like 2 indices, then we have to.
When you check for the loops, you have to do it in the small signal sense, right?
Small signal sense, yes, correct, exactly. Yeah, the loops when you're checking for it, because all of the transfer functions we are writing, that's a good question, but the reason is that we are writing all the transfer functions in small signal sense because the large signal, defining a transfer function technically is meaningless for a large signal because it's a nonlinear system anyway. Writing a transfer function of that sort is meaningful for a linear system to begin with. There is something you can do for nonlinear systems, which becomes, if you think these things are elaborate and complex, wait till you see Volterra series and Volterra kernels. There are integrals of impulse. They are convolution of nonlinear integrals. So it's like just like they're going inside each other. They're nested nonlinear convolutions. So, but you can actually deal with a nonlinear system with that. It's called Volterra series. We are not going to teach that, but just like it's good to know that there's such a thing exists. If you really, really need to do something with that, just look it up. But okay, let's go back. So this is a linear circuit. This is an entirely linear circuit we are looking at right now, and it's a linearized circuit. So let's look at the time constants. So what are the time? Well, first let's calculate the H0. H0 is usually comes first. So when both of the capacitors are gone, it's a low frequency calculation, like all the other calculations. It's basically a divider, right? Since this current is 0 at DC, there's no voltage drop across here. So if this is V in, this is V in. So you have a voltage divider here. So you get R2 over R2 plus Rm. Right? And the same thing. OK, so now let's calculate the other ones. Tau 1, 0, or tau pi 0, and tau mu 0. So what is tau pi 0? What is the resistance seen across here when the other capacitor is not there, it's open circuited? Not exactly. So this is where you have to be very careful about this thing, because there's current going also in this direction, right? We derived the general calculations for this, right? Because there's current flowing through here and there too. If you apply a test voltage here, it's not just the Rm. And we did calculate the general impedance resistance seen from 3 different ports of a transistor. You remember we derived this case, it was a homework problem last quarter. So in this case, it would be basically what you see is going to be R1 plus R2 divided by 1 plus GMR2, if you remember those calculations. Right? So it would be, that resistance is going to be R1 plus R2 over 1 plus GMR2 times C pi, which you can also write, if you prefer, write as Rm C pi times R1 plus R2 divided by Rm plus R2. Right? So that's the time constant for that one. And what is R mu? So what is tau mu? Or R mu 0? The resistance seen by this guy. That's a simple one, right? Because this end is grounded, and there's no current going in this direction, so the resistance seen into this guy is infinity. So you just see R2 to ground, right? C mu just sees I'm sorry, R1, not R2. It's R1. I misspoke. R1. So this is going to be C mu R1. So these are the 2 time constants associated with R1, R pi, and R mu. Now, we need to calculate one more if you want to calculate the denominator completely, if you want to calculate the B2, right? Which one would you pick? Which one would you short circuit? I would like to short circuit it here if I can, right? Because then it also forces this to be 0, and then this guy disappears too. So the one to calculate, probably, I mean, you don't have to use this one, is R mu pi, tau mu pi. So I want to get the pi in the numerator, in the superscript. So what you have here, then it's going to be C mu times something. So what is that R mu pi? R1, right? When you short circuit this one, the resistance seen across here is R1, right? So is that all you see when you short circuit C pi? Parallel R2, right? Yeah. So it's going to be C mu times R1 parallel R2. Okay. And then we need to calculate one more thing if we want to calculate everything. So we know the h's, right? So there are a bunch of them, but let's calculate them. What is h mu? H mu is the transfer constant when C mu is infinite value, shorted. What happens if you short circuit that C mu? Nothing gets to the output, right? So this is going to be 0. How about h pi? What is h pi? When you that's a non-zero one, right? I mean, so to this you short circuit it.
The R1 to R2.
Yes, then you get the voltage divider between R1 and R2 because this is short circuited. This guy disappears anyway because that current is 0. So you get basically what? It's R2 divided by R1 plus R2, right? And then there's the h mu pi, which is what? If they're both short circuited or infinite valued, what do you get? 0. So now, in both cases, well, I didn't even finish that case, so that example, so I have to go back to that and finish it. Well, at least in this case, as far as we are concerned, we are done. As far as I'm concerned, we are done. You can try to write the transfer function explicitly, plugging these things in, and we can do it, just for completeness. But this is done. Now, this one was not done because I forgot to do something. I didn't calculate the rest of the transfer constants, right? So let's do that, and then we'll write the transfer functions for both of them, and then discuss that. So I'm going back and forth a little bit here, but that's okay. So for this example that we did before, what was this? H1, what is H1? 0, right? Because you short circuit this guy, nothing goes to the output. So this is 0. What is H2? Yes, no, H2 is non-zero because you short circuit this one, you have a resistive divider between these two. It's R2 over R1 plus R2. And there's the so-called the H12, which is also 0. So again, here we are done as far as, you can think about it as being done at this point. Because you know everything you need to know. Now, if you really want to calculate the transfer function and write every parameter in terms of S's and all those things, you can do it. But there's actually more information in this form than if you try to put a compounded form and all those things. We can write it. That's fine. It's not a problem. So if you write this, the numerator would be what? The only non-zero term in the numerator would be due to this one, right? So what you have is R2 over R1 plus R2, which is H2, times what? So the first term in the numerator would be the A1 term, times tau 20, right? Correct? So it would be tau 20 H2 times S, right? That's the only non-zero term that you will get in the numerator. It would come from this sum, right? So what would that be? The R1 plus R2's cancel. You get R2 C2S in the numerator. And in the denominator, you have the 1 plus B1, which is the sum of these two, right? The zero value time constant, which you can write it as whatever, R1 C1 plus R2 C2 plus R1 C2 S plus, then you get this guy in the denominator, one of these, which is simple. So R1, R2 C1 C2. So it's R1 C1 R2 C2 S squared. So this is the transfer function if you really want it. But already this is more useful because it's broken down into pieces that you can look at independently. You can see where they're coming from, each one of these components, as opposed to just some aggregate of some of the products and things of that sort. So I'm in favor of looking at it this way. But if you want, you can always convert it to that form. Same thing here. Now, here we can actually do a little bit more analysis, which is can be interesting in terms of what it looks like. So if you assume that R2 is much greater than R1, and R2 is also much greater than Rm, then these things simplify a little bit. If you assume that, you will see that this one, tau pi 0, roughly becomes Rm C pi, right? Because this kind of becomes 1, because if R2 is dominating. And in this combination, you will get roughly R1 C mu. Yes?
Explain the denominator again.
The denominator of that one?
Yeah.
Yes. I'll explain it in a second. Just let me finish this one, and I'll go back to that for a second. So, and then, OK, so that would be these guys, and then you can just calculate the product this way if you want. In fact, actually, before you do that, you may want to calculate this product, which is basically tau pi 0 tau mu pi, because that product simplifies a little bit, because you have this one, Rm C pi, R1 plus R2 over Rm plus R2 times R1 R2 over R1 plus R2 from this term. These guys cancel. So you will be left with R2 that will cancel. So we'll end up with an R1 C pi if these two conditions hold. If R2 is much greater than both Rm and R pi, this will become mostly R2. But cancel that one. What is left is going to be R. Yeah, no, yeah, I messed it up. Yeah. Yeah, this would cancel that one, and then there has to be a C mu, which I forgot to put in. So it would be Rm R1 C pi C mu, right? So that would be that one, well, approximately. And then you have those terms. So you can basically just plug them in now. And then the other term, in the numerator term, you have this times that. Again, these two cancel. So if you want to calculate the h pi tau pi 0, which would be one of the non-zero terms in the numerator, it would give you, these guys cancel. You get Rm C pi R2 over Rm plus R2. But you also notice that this is simply H0. So you can write it as H0 times Rmc pi. Why is this a useful form to write? Because if you factor H0 from the numerator, you're left with the unity gain, the DC gain is factored out, right? So it allows you to do that. If you can write any of the numerator terms in terms of H0, do it. Because it allows you to simplify the factorization. So if I do all of these things now, then what we're going to end up with, h of s is going to be approximately h0, which is written there, times 1 plus Rm C pi s. Okay? Now what do you get from the denominator? You get 1 plus Rm C pi plus R1 C mu times S plus Rm C pi R mu, R1 C mu S squared. Now, if you look at the denominator carefully, you will see that this actually can be factored. This is an approximation, but it can be factored, right? And when you factor it, one of the factors is actually this guy. So again, when you write that factorization, it becomes roughly H0, well, from there to there it's exact, but this is the approximation, is 1 plus, what is left only is the R1 C mu S. Now, this is an important implication for the circuit. So you can see that if these conditions hold, if R2 is much greater than R1, the circuit is really dominated by this guy, this time constant at the input, R1 C mu. Why? Because what happens is that this combination of the zero that you created here, which is, by the way, around the ft, if you look at it, Rm C mu, or around omega t more accurately, around the cutoff frequency, is also around where the zero is. The zero and the pole are around the same thing. So there's a zero and pole combination. They're not exactly at the same place if you calculate them, but they're close. That for the most part, they cancel each other's effect. And you're dominated because as this starts getting worse through the capacitor, again, there's more, as your frequency goes up, more of the signal goes through the capacitor than goes through the resistor. So it is really the time constant associated with these two, the R1 C mu, that usually can dominate the response of this thing. Because that pole and zero are high frequency, and they're close to each other, and they're around the cutoff frequency. But that's another way to think about the frequency response of a source follower that typically, depending on how you implement it, can be a higher frequency response, right? Okay, so you had a question about how I calculated this. Any questions on this before I go back to that one? No. All right. So what was the question exactly? So which part was? The denominator. Which part? Numerator. Yeah. Okay. So the numerator. So how did we calculate that? Let's look at these terms. You have the only non-zero term, H term, is this guy, right? So this pairs with what? The A. That's part of the A1, right? So you have tau, you have to find the tau 20 and H2. So this is this one, and tau 20 is this guy, right? If you multiply them, R1 times R2 cancels, so you're left with R2C2S, right? Any other questions about these examples? Okay. So now let's take these examples, and we saw them so we can calculate stuff this way. But now let's go back to our specific example of a second order system. Now, we know that the response of a second order system in general can be written as something that can be expressed in terms of natural frequency and the quality factor, or the damping ratio, right? Those are the parameters that you can find. More explicitly, h of s can be written as some numerator function, which we'll not worry about for now, divided by, and some gain, 1 plus s over q omega n plus s squared over omega n squared, right? Where these are the natural, omega n is called the natural frequency of the system, and then the q is the quality factor of the system. So the other way to write this is also you can write it in terms of damping factor zeta. In this case, you write it as 2 zeta over omega n s plus s squared over omega n squared. And from this, you can easily see that q is 1 over 2 zeta. Zeta is sometimes called the damping factor. So what is Q, by the way? What is the quality factor in a circuit? The quality factor, what's the definition of quality factor in a resonator? The ratio of energy stored divided by the energy dissipated times 2 pi. Yes, but yeah, correct. So Q is the ratio, is defined really as the rate as 2 pi times the ratio of the energy stored in the resonator and divided by energy dissipated per cycle in each cycle, right? Which you can also write, you can reorder it as omega, natural frequency, times energy stored divided by the power dissipation. You can write it that way. So that's kind of like a measure of how resonant something is, right? How much, the higher the quality factor, the more cycle it takes for the energy to get dissipated. So this is a metric of usually kind of like showing what the transfer function of the system looks like. And natural frequency is also a useful thing to know, I mean, because it's natural, it shows you where the natural frequency of the circuit is. And the transfer function of a system that has a quality factor, if it's a low-pass system, but it has a high quality factor, can be something like this, right, versus log of omega, if you look at the Bode plot. And this peaking usually is around Q in absolute. So of course in dB you have to calculate the 10 log of that to get the, or if the magnitude actually, calculate, if the magnitude amplitude, it has to be 20 log of that, 20 log of Q in dBs, right? Now, what frequency does this happen at? It's not exactly at omega n. It's slightly off, right? This frequency is omega n times 1 minus 1 over 2q squared. Now, if your q is large, this error is going to be small. So you can say it happens roughly around omega n. But if your q is small, then the other thing to think about is q also is a good number to look at if you want to find out, or also related to that zeta, if you want to find out if your poles are complex or real. So what is the value of q above which the poles would be complex? This is a good number to remember. I mean, you can basically write the quadratic equation or try to kind of factor it or something like that. It's q of 1/2. If your q is above 1/2, your poles are complex. If your q is below 1/2, your poles are real. I mean, it's basically just solving the quadratic equation, right? And finding what when under the square root, we get negative numbers under square root, or when the square root basically becomes 0. That's the point where switching happens. And you can see it's the q of 1/2. So that's the point where it switches from real poles to complex poles. But anyway, so that's good. So that's q, and then omega n are the two things we want to calculate. But now, if you write it in this form and compare it with this form, is there a way to express these q and and omega n in terms of the time constants themselves, right? We can, right? Because now we can express these things in this form. So let's do it. So for example, okay, let me pick a different color. So let's start with B2, because that's a simple one, right? We know B2 is 1 over omega n squared, right? So that from these two you can easily see that for second order. So B2 is equal to 1 over omega n squared. Therefore, omega n is 1 over square root of B2, right? But B2 can be written in this form. So you can actually write it as 1 over square root of tau 1, 0, tau 2, 1, which would be also equal to 1 over square root of tau 2, 0, tau 1, 2. So if you want to find the quality factor of a second order system, you just need to calculate the two time constants, one of the zero value ones and one of the second order ones. And you can express it in those terms. Also, if you want to calculate Q, let's look at the Q, right? So Q, or more, let's look at the 1 over Q. So we know 1 over Q omega n, right, is B1, or B1 is 1 over from this one, right? So now what we can do, I can say 1 over Q then is B1 omega n, which would be B1 over square root of B2. And if you want to write it in terms of time constants, you can actually write it, let's just do this here. So what is B1? B1 is essentially the sum of these two time constants, right? So it's tau 1, 0 plus tau 2, 0 divided by square root of tau 1, 0, tau 2, 1. But if you look at this carefully, you can actually write the first term. You can simplify this as tau 1, 0, square root of tau 1, 0 over tau 2, 1, right? But for the second one, you can actually use this identity and this equality and write the second one as square root of tau 2, 0, tau 1, 2. So that's basically, essentially, 1/2 of, that would be 2 zeta, right? You can write this also as 2 zeta. 1 over Q equals 2 zeta is that. So you can actually, using this time constant, you can directly calculate and evaluate what the transfer constant, the quality factor and natural, and the zeta are. So let's do a quick numerical calculation, right? I mean, let's do something simple and then see how it works out, how does it compare with the simulation, for example. So let's look at the example of, so let's use our source follower. We're going to make it even simpler. So let's make a simple source follower just to see this effect, to make it even more pronounced. So let's say you just have the R1. Let's say you have just the resistive load, you have a capacitive load. So you have R1, the input resistance. You have this device, and then this is your output. So basically, which means that you had to use the current source, and this is V in. And then you have a capacitor here, CL, and then you have a capacitor C pi. So let's forget about C mu for now. Okay. And let's just pick some typical values. Let's say a C pi, so we're going to make this numerical, right? So C pi equals CL equals 50 femtofarads. And then GM of 20 millisiemens. Oh, not 2 millisiemens, 20 millisiemens. All right? So you have these two. And then what do you have? So, and then R1 is 2K. 2 kilo ohms. So let's calculate the time. I mean, the time constants are trivial here, right? So we have, so let's do it very quickly. H0 is going to be what? H0 is 1, right? Because this resistance is infinity. So you have H0 of 1. H pi is, now what? It's still 1, right? HL is 0, because if you short circuit this, nothing is at the output. And H pi L is also 0. And both of them are short circuited, right? So those are the transfer constants. The time constants, tau pi 0. Now you don't have a resistor here, so all the current has to circulate, so it's Rm, the resistance seen by it, right? So it becomes C pi Rm, tau mu, well, there's no mu. Tau L0 is what? What is the resistance seen by CL when this one is open? It's also Rm, right? You see looking into the source. So it's CLRM. And you need one more. You can pick the one that you like. I would say tau L pi. If you just short circuited, what does this guy see? It sees R1, right? So it's CLR1. So we can put them together and all those things, but let's plug them into these guys and see what the numbers would be. So in terms of omega n, what we need, and let's put some numbers here, by the way. So we said these are both 50 femtoseconds, and 20 millisiemens corresponds to 50 ohms, right? So 50 femtofarads and 50 ohms is 2.5 picoseconds, right? Each one of the time constants is 2.5 picoseconds, I believe. Yes. So this is 2.5 picoseconds. And this is 2.5 picoseconds. And then this guy is 2 kilo ohms times 50 femtofarads is what? You get 50, sorry? Yes. Yes, this is 100 picoseconds, right? It's 50 times 2. Sorry, it's 50 times 2, it's 100. Yeah, 100 picoseconds, that's correct. So, and then, therefore, if you plug it into this guy, what do we see? So we need the product of this tau and this one, right? So this becomes 250 picoseconds squared, right? So it becomes 1 over 250 picoseconds squared. And you calculate that, you will get 2 pi times 10 gigahertz. Now, similarly for the Q, or 1 over Q, well, you can calculate 1 over Q or Q. So you have the B2 already. So let's make it simpler. So you need to calculate B1. B1 is the sum of these two, so it's 5 picoseconds. So it's 5 picoseconds times this. And when you do that, you get a Q which is square root of 10. So then you get a Q that's square root of 10, which is roughly 3 point whatever, 16? Yeah, 3.16. So this is a basic calculation. You can estimate the Q and the thing. So how much peaking do we expect in dBs from this? What is square root of 10 in dBs in amplitude? 20 log of square root of 10 is what? Is 10 log of 10, right? Which is what? It's 10. Okay. So now let's look at the SPICE simulation associated with this. So you can see the amplitude and phase response of this thing. And if you look at that, what you will see is that you can see that it's happened, there's peaking happening around 9.8 gigahertz, which is close to omega n because the Q is not too far. So that's, for example, 9.8 gigahertz is the maximum peaking. And the maximum peaking that's happening is essentially 10.2 dBs, as opposed to our calculation which predicts 10 dB. And you can see that it has also, you can clearly see that it has complex poles with a high quality factor, both from the peaking and also from the phase response, because you can see the phase response is much steeper than what a typical real pole would produce, or pair of real poles. And then you will see the effect of 0 that brings it back up. So you can see that the phase dives down and peaks back up. And you can see that also in the amplitude response. You can see the slope of amplitude response becomes shallower going forward. All right? So you can actually see that you can get a fair amount of useful information from this. We can do one more example quickly, and then of the second order system, and then we'll do, next time we'll do more discussion of the applications of TTC and how it's applied. So let's do one more quick example of TTC in the second order system. So I'm going to erase these. And we want to do something with inductors. Just make sure that you're comfortable with them as well. And we want to also make sure that it's something that is meaningful. It's not just some random combination of inductors and capacitors. So we'll do another second order system. Okay, so the circuit we are going to look at is a common source amplifier with an input voltage directly applied to the gate, Vn, and then going to a resistor R1. Then there's a parallel LC driving a load resistance RL, and this is V out. Right? So this is a relatively simple circuit. We can look at it and we can see what is the transfer function at DC, at 0. At 0, do we get something through? Yes, right? Because you have the inductors shorted. At infinity, do you get something through? Also, you get something through. So it's an interesting circuit, right? There's some frequency at which something may not go through. But let's find out how it behaves. So what are the time constants? So the first calculation really is the H0, right? So what is H0? At 0. When basically what H0 means, you zero value everything. You zero value the capacitor, it's an open. You zero value the inductor, it's a short. So what's the gain of the circuit? Well, the gain from here to there is GMR1. Well, but it's not really from here to there, because in that case it's GMR1 parallel RL. That's the resistance you see, right? So if you look at H0 is negative GMR1 parallel RL, because this is going to be shorted at that point. How about, okay, so let's look at the taus. So what about tau C0? So we have only one capacitor and one inductor. I just call it C and L, tau C0. So tau C0, what's the time constant of capacitor C when all the other values, all the other elements are zero valued? Zero, right? Because if this guy is zero valued, it's shorted. So this time constant is 0. What is tau L0? The resistance, what is the resistance seen by CL when this guy is, so if this guy is zero valued, this is not there. So what is the resistance you see across here if you ignore RO? R1 plus RL, right? So it's basically L divided by R1 plus RL. Well, let's write it more explicitly, L over R1 plus RL. Because it's a time constant associated with the inductor, so it gets L over R. Right? So, yes, fine. So you need to calculate one more. One of those combined time constants. It's the second order ones, right? So we can calculate tau CL. What is tau CL? The resistance seen across here when L is infinite valued. When L is infinite valued, it becomes open circuit, right? So now what you see is just two resistors now. So it becomes C times R1 plus RL. And if you use this in combination with that guy, you get tau L0, tau CL. And these two cancel, you get LC. Now, if you had calculated the other one, you would see that it would have become infinity. So that would have become infinity times 0. which you can actually disambiguate by adding kind of like an artificial resistance RS or RX, something here, and set it to 0 after you do the calculation, and you will get exactly the same result. But generally pick the one that's associated with the non-zero one, because then you're not going to get an infinity. You can do that, you need to do more work. Now, how about the remaining time transfer constants, right? So so let's see, what is HC? When C is infinite valued, well, and L is 0 valued, so both of them are shorted, so you get the same thing, right? You get H0. What is HL? If L gets infinite valued and C is 0 valued, right, so you get basically 0. And if both of them are infinite valued, do you still get 0? Because L is infinite valued, it's open. C is infinite valued, it's short. So you get H0, right? So now we have these things. We are essentially done, but let's write the transfer function. So H of S is, so I can factor H0 from the numerator because it's everywhere, right? So from the first term, I will get H0, I get 1. The second order term, A1, will have H0 times, so I have HC times tau C0 S. So this is basically tau C0 S. But tau C0 is 0, so that's going to go away. So I don't have A1. Does it mean that I don't have an A2? Not necessarily. So some of the intermediate ones could be 0. So how about A2? A2 is going to be this product times HLC, so which is H0. So it basically what is left is going to be LCS squared because I factored the H0 part of it. And in the denominator, what do I get? We get 1 plus B1, which is what? The sum of these two, which is L over R1 plus RL S, plus this guy times S squared plus LC S squared. So you can see that you have a complex pair of complex zeros. Actually, in this case, you have a pair of imaginary zeros, not purely not complex, just pure imaginary zeros at the LC frequency, which means that if you drive it as at the omega of 1 over square root of LC, nothing will go through. It will just completely block that. If you drive it with the sinusoidal input at the frequency of omega 1 over square root of LC, then it's a band stop. This is a notch. It will block it completely. Of course, you don't have an ideal L and ideal C. They always have some resistances associated with them, so the blockage would not be perfect in a real circuit, but it would be still there. Okay, so that's another example. Any questions? All right. Thanks.